Maths Master Blaster. This is part 2. Let's look at section 9.2. In the diagram below, L is the point on KM, right? And then of triangle KMQ. Right, perfect. Then N and P are the points on the side MQ. Then we have N and P that on MQ. Then we further given that NL, it is parallel to PK. And again, we given further that LP, it is parallel to KQ. Right. And then on the side MQ, we given that MN, it is 20 units. And again, NP, it is 12 units. That is based on the given statement. Now, looking at the question 9.2.1, they say determine the length, the ratio of KL over LM, not the length, in the most simplest form. Right. Now we know that KL divided by LM, that will be equal to NP. NP divided by MN. Because if we can look at triangle LMP, we'll see that LM, it is parallel to LP. That gives us a proportionality theorem. And then the side are in proportion. Then we'll have 12 divided by 20, which 12 is given by 4 times 3, and 20 by 4 times 5. And then 4 will divide 4, and then we'll be left with 3 will be equal to 3 over 5. And then you state your reason, which is prop theorem, or a line drawn parallel to one side of triangle. We can write it in this form, line drawn parallel to one side of a triangle. Yeah. Okay. Now, let's move to the next question. 9.2.2. Calculate the length of PQ. PQ. That is the given PQ that we need to calculate the length of it. Right. So, looking at PQ, we can see that it is in proportion with the other side. But however, we have that other side to be equal to KL divided by LM to be 3 over 5. Then we can say let KL be 3x and then LM be 5x, because we don't know the actual value of x, but we know that the sides are in proportion. Then we have triangle KMQ, and then we can now use prop theorem because we know that the sides are in proportion, because a line drawn parallel to one side of triangle, which is LN, that's parallel to KQ, right? Now, we can go and say now we have KL divided by LM or ML, which it is equal to PQ, which is what we are looking for, PQ divided by, and then that will be MN, MP. Then there is a proportionality theorem, right? And then we know that KL divided by that will be 3x over 5. We don't know the actual value of x, which it will be equal to PQ divided by, and then we're going to add MN with NP, which it is going to give us 32. Right. Now we work that out. So multiply both sides by 32, so that we can multiply the other side with 32. Then we're going to get 1. 32 divided by 32 is 1. And then 32 multiplied by 3 over 5, that will be equal to PQ. That will be equal to PQ. Then now let's press our calculator and see what are we going to get. 32 multiplied by 32. Then 3 over 2 multiplied by 32, we get 19,2. That is 19,2 units. That's correct. So now determine the ratio of KQ over LP in the simplest form. Okay. Now let's look at KQ, which it is what we are required to get over LP. And if we can look at the two, we'll now see that we're going to have KMQ, which is a triangle that holds KQ, and then we also have LP, which is in triangle LPM. Then by that now we can see that angle L is equal to angle K, and then angle P is equal to angle D in that case from the both two triangles. Then now you can say triangle, which is triangle LMP, it is similar to triangle KMQ. Those two triangles with triangle LMP. Those are angle. They are similar. Then that tells us that their sides are in proportion. Meaning now I can say that KQ divided by LP, which is equal to MQ divided by MP, which it is equal to, then we're going to have 12. Good to remove everything. 52. We add the whole sides, that will be 51,2 divided by, and then we're going to take MP, which is going to be 32. It's already calculated, and let's see what we get. We're going to have 51.2 divided by 32, that is 8 over 5. Then we get 8 divided by 5. Right. Okay, now let's look at the last question of Euclidean geometry, paper 2, which is question 10. In the diagram, O is the center of the circle BCEF, and then ABD is a tangent, right? Let me remove that. Those are the circle, where the circle lies. And then, okay. Then we have our tangent to a circle at B. That is our tangent. And COA, it is a diameter. And then there we go, that is our diameter. And the line AFO, we have line AFO, which BC are drawn in the parallel. We have AO, which is parallel to BC. Okay, now the first question, prove that BG, it is equal to EG. Let's look at it. Now, looking at it, we know that B3 that will be equal to 90 degrees. That will be angle subtended by the diameter or angle in semicircle, right? Angle in semicircle. That was supposed to be I, circle, right? Now, we know that angle in semicircle or angle subtended by diameter is subtend 90 degree. And B3, that will be equal to G1. That will be equal to angle G1. Reason being, corresponding angles are equal. That is, corresponding angles are equal. Let me write it down for you. Corresponding angles are equal. Perfect. Are equal. Why are they equal? Because we have parallel line A. Let me just remove that. We have parallel line AO that is parallel to BC. Take note of that. That is parallel to BC. Right. Okay. Let's continue now. We now know that G1 it is equal to B3. Now, G1, the given angle G1, it is equal to G2. If we can take G1 and add it with G2, let's add them together. Let's work it out. If we can take G1, we add G2, then we're going to have 180. Those are angles on a straight line. Angles on a straight line, they add up to 180, or they're supplementary. And then we know that G1, it is 90 degrees, and then G2, that's what we're looking for, and that is equal to 180. Now, by subtracting both sides by 90 degree, then we're going to have G2 to be equal to 180 minus 90. That will give us 90. That will be G2. Right. Then, G1 and G2, they're equal. That tells us that BG, it is equal to EG. Why? Because a line drawn from the center of the circle and forming a 90 degree, it does bisect the chord. So a line from the center perpendicular to the chord, it bisects the chord. Now, let's move to the next question. Question 10.1.2, prove that AEOB, it is a cyclic quad. Right? Now, for us to prove that indeed AEOB, it is a cyclic quad, let's look at it from the diagram. We have ZAB going up to E, D, A, O. That's what we're trying to prove, that is a cyclic quad. Now we need to show. Okay? By doing that now, we can say B4, it is equal to angle E. Reason being tan chord. Angle subtended by the tan and the chord is equal to angle subtended by the very same chord at the alternate segment. That is tan chord theorem. And then again, we have B4 again to be equal to, let me remove everything there. Okay. Let's draw those parallel, let's outline the parallel lines. Take them out. Here we have parallel line AO and we have parallel line BC. It forms F, corresponding angles. And you see that. Then we're going to have B4 to be equal to A. Let's take a note of that. Let's write it down. We have B4 to be equal to angle A. Reason corresponding angles are equal. Let me write it down for you. Corresponding angles are equal. And then we have parallel line AO parallel to BC. Right. Okay. So now, since we can see that angle E, it is equal to angle A, and then both they equal to B4. Then now we can conclude that AE OB indeed is a cyclic quad. Why am I saying it's a cyclic quad? We have proven above that the converse angles in the same segment. Right. Perfectly fine. Now, 10.1.3. We need to prove that triangle OEG, it is similar to triangle BAG. Right. So what we need to do now is to take our triangle OEG and take our triangle BAG. Let's go. BAG, that is the other triangle. So now we need to prove that the two triangles are similar. Let's check it out. Angle A, it is equal to angle EY. It is proven in 10.1.2. And again, let's look at angle G. We have G1 and G3. It is equal to G3. Those are vertically opposite angles and they are equal. And then we have now angle B in the other triangle, which is going to be ABE, and triangle angle O2. Those two that equal, we can call them B1, B2. Angle B1 plus B2, it is equal to angle O2. We can say third angle, or we can also say we have proven that AEOB, it is a cyclic quad and they're in the same segment. Right. So now we can conclude that triangle OEG, it is similar to triangle BAG, reason being angle. Right. Okay. So now if BC is 10 units, we're now going to 10.2. 10.2. If BC it is 10 units, perfect. Let's just make some space. Question 10 units. And then AG, it is 35. And then calculate the length of EO. Right. Now we can now say that OG, it is equal to half of BC. Right? That follows a midpoint theorem. Okay? that follows the midpoint theorem. And then we have 1 over 2 of 10 that will give us 5 units, meaning our OG, it will now be equal to 5 units. OG, it is 5 units. Then, right, our OG now, looking at the similar triangles proven in 10.13, OG divided by BG, it will be equal to OE or EG divided by AG, which it is the same thing as EG or OE divided by BA. Right, that follows the proof of 10.1.3. We have proven that the two triangles are similar. Right, similar triangles. Can use that as another reason. Now, what exactly are we looking for? We are looking for OE, but it won't lead us to what we are looking for or what we want. Now, we have EG, which can help us to find OE, because we now have OG. If we find GE, then we can be able to calculate OE, because we know that G1, it is 90 degrees. Right. Okay, so now I can say BG, it is equal to GE. It is proven. Then I can replace BG there with GE. Then I'm gonna say OG divided by GE, because it's equal to BG. And then now I'm going to use GE instead of EG. Still the same thing, divided by AG. Right, now I have OG, that is 5 units, divided by GE, that's what I'm looking for. And then we have GE again, divided by AG. That is 35 units. Now, going to cross multiply. Then GE, I'm going to have GE squared, which is equal to 5 multiplied by 35. Then from there, you can press a calculator. That will be 5 multiplied by 35. That give us 175. Then we're going to have GE squared, which is 175. 175. Oops, let me put a square there. Right? Then we have GE, you square both sides. Then you'll have GE to be equal to press square root of 175. That gives us 13,23. Then we're going to have 13,23 units. Remember, we are not looking for GE. However, we are looking for OE. Now we can use Pythagoras, because we know that Pythagoras said OE squared, which is the hypotenuse squared, equal to OG, that is the adjacent, plus the GE, which is opposite, squared. Then that is supported by Pythagoras theorem. Oh, oops, why did I write GO? That was supposed to be Pythagoras theorem. Right. Okay. Now, OE squared is equal to, then OG, that is 5 units, plus, then we have 13.23, that is GE, squared. Then everything it is equal to OE, it is equal to, then from there we press the calculator. OE squared is equal to, press the calculator, let's see what we get. We have 5 squared plus 13.23 squared, then that will be 200,03. Let me write it down. it'll be 200, 0.0329. Okay, so we're looking for EO. And then our EO will be the square root of that. EO will be equal to 14,14 units. You've squared both sides. And then that's why we have OE to be equal to that. Thank you.